Okay, yeah. So topological materials are very new and very interesting because they have many potential applications already in the weekly interacting regime. I'm gonna mention some of them because I think they have not been discussed yet. So, for instance, they are environmentally friendly technology because they have in all these transfer effect, quantum anomalous fall, spin Nernst effect, will have a constant conductivity, and this is very interesting for applications, very robust surface state with low dissipation at room temperature, etc. They are also very interesting for energy conversion because the surface state can be utilized as catalytic agents. There are several proposals too, but all these fields are very, very new, so there is a lot of work in progress. When we have chiral structures, they are also, they have very interesting and non-trivial spin textures, so we can also use it for spintronics and detectors. And when in the superconducting states, we can find Majorana modes, and these are non-Abelian anions, and we can use it for the braiding in quantum computing. So they have many interesting applications, but we need to find materials that actually can host these physical properties to be used as platforms. So we talk about topological materials. We say that they are insulating in the bulk and conducting in the surface, but there are different topological phases. Not all have the same states under the same symmetries in the same dimensions. There is a crossover between dimensionality, symmetries, and topology. And here I'm going to mention a few of them that you know a little bit about topological phases. So the quantum Hall effect, we all know it. It was discovered in 1980 by von Kitchen. And the interesting features related to symmetry, dimensionality, and topology is that we need to break down the result symmetry in this class. In this case, it was done with a large external magnetic field. It only exists in even dimensions. And we have one polarized edge state. The next example is the Haldane model that it defines insulators. It's the quantum Hall effect with an intrinsic magnetic flux. And again, we need to break the universal symmetry, which is broken by magnetic moments. And it only exists in even dimensions. So we have, in the same way, a spin polarized quantized edge state. And then we have the quantum spin Hall effect that was predicted by Ken and Melle, and it started the field of topological materials, where they put, let's say the idea was to put two Haldane models, one on top of the other one, with different opposite spin, positive and negative, glued by time reversal symmetry. And many people thought about this problem, but Kane and Melle found the way to diagnose topology. So these are the C2 topological insulators, and they have two helical edge states, one for spin up, spin down, or positive and negative, and they exist in every edge and every surface of the material, as contrary to the quantum Hall effect, but only exist perpendicular to the magnetic field. So these two cases are protected by a topological order. These two, in this case, it's protected by time reversal symmetry, but also crystalline symmetries can protect topological phases. That was predicted by Liang Fu in 2011. There are surface states that can be protected by mirror symmetry, and in this case, we will only find surface state in the surfaces where the mirror is protected. It's not broken. So this is a bit when Kane and Melle give a recipe on how to find topological materials that could exist in the presence of strong spinor recoupling and at room temperature. Let's say for magnetic, for topological material started. The first one was mercury telluride, then there's 3D TIs with selenite and the family that are very famous. Quantum anomalous Hall system was proposed in 2013, which was an analogy of antimony telluride with chromium. thin telluride and light telluride were proposed as mirror cell insulators. Then with the symmetries, with the protection of the symmetries, the Dirac semi-metals and the Weiss arrived. Then there were the high order nodal semi-metals, nodal lines, and in 2018, there were insights on looking to higher order TIs. So there was a thrilling activity looking for topological materials. However, after like 40 years since the discovery of the quantum Hall effect, for the order of 300 topological materials were predicted, and usually when they were predicted, since they were in the weakly interacting regime, the growing and detection was happened immediately after. So for many years, it was believed that they were very exotic, a rarity in nature, and that finding a topological material was something very weird. So the way people were looking for topological materials was integrating the very phase in a surface, and we are in 3D systems, we need to do it for every surface. So it was computationally very expensive, and it was not real understanding on why this was happening. So what I'm going to tell you about is a framework that we already developed 5-6 years ago, and it allows us to actually detect topological materials in a very fast way. So I need to go back to the beginning, but we keep adding more and more systems to the database, and at the end I will discuss the new system. So in order to find topological materials in an effective way, we need to first define what is a trivial material and not topological material. This is defined by the atomic limit. So the atomic limit can be expressed by the Wannier function. So the Wannier functions are these wave functions in, the Wannier functions are a set of functions in real space that come from the Fourier transform of the block function in reciprocal space. And they are very interesting because they have, let's say, a maximum when we plot it in real space. And actually, this maximum, this Wannier center that is called, is proportional to the very phase. So actually, a Wannier basis can give us whether we have a finite or zero very phase. And when we have an atomic limit, which means a trivial state, what we have is the Wannier center atomically localized in the atomic site. So when this happens, our bands are going to be trivial. And this is very important because when this doesn't happen, it means that our bands are topological. The church might be doing different things depending on the topological phase and the relation of the wave function, but it's not going to be trivial. Okay, so, but again, this integral is not something computationally, well, it's less and less expensive, but it's still linearizing a Hamiltonian is not something straightforward yet. Computational methods are not there yet, but there is a methodology that considers all the crystalline symmetries of the crystal in the 230 space groups that can actually diagnose whether a material is topological or not by performing 20 minutes DSP calculation. So this is the topological quantum chemistry that I explained already yesterday. And it's based on a concept that is a mathematical concept that is called elementary band representation that was introduced by Zach and Michel in the at the end of the 20th century. And what it actually relates Brooks theory with atomic limit of Wannier basis. So these three ingredients, orbital, atomic site, and the lattice, or the reducible representation of the orbitals in real space, the Bikov position and space group, these three ingredients together, when we have the maximal position of all of them, describe a set of bands in reciprocal space that are going to be connected. And this is something that is given. It was proved in the papers of Zach, and we know it's like that. And it's like that always, because these three ingredients imply that the orbital is localized in the atomic site, So they describe an atomic limit. And when they describe an atomic limit, the charge is maximally localized in the atomic site, so the bands have to be connected. And the interesting thing that we discovered during this work is that these bands that are connected can be described by the reducible representation in reciprocal space. And this is unique for these three ingredients. So whenever I have PC orbitals, honeycomb lattice, and hexagonal space group, I can tell you without doing the calculations what are going to be these spheroids at the high symmetry points. So as I said, when we have a system that has Vannier-Weiss exponentially localized, it's trivial, but when this doesn't happen, it's not trivial. And if it's not trivial, it's topological. How can we tell this from this setup? We can tell this when I find a gap here. If my three ingredients describing the bands happen that in reciprocal space have a gap, then my bands are going to be topological. But in order to do that, I just need to calculate the wave function at the high symmetry points. And this in DFT for 3D bulk, for the majority of materials, is done in 20 minutes. So by combining this new knowledge, computational physics, initial calculation, and group theory, we could actually scan a very large material database and diagnose topology, as I said, very fast. So we developed an algorithm interfaced with a DFT code, and we actually run it and diagnose topology for all these materials. So we found that actually, contrary to what was believed, that they were a rarity, they are very common. Topological materials are very present in our nature, in a sense that only less than 50% can be diagnosed as fully trivial. And even in trivial cases, we can have obstructed atomic limit that they have non-zero Berry curvature, even though it doesn't lie. But this is another story. And even if we look at any filling, if we go through the full spectrum, because we were also thinking, well, maybe it only happens at the valence electrons when we are close to the Fermi level. It happens that we also have a lot of presence of topology or finite Berry curvature. It's that, no? I don't know.
So doesn't have a slide to go.
Yeah, but it's not going.
Maybe
Okay. Okay. All right. So 50% of materials display topology, and 80% of materials have at least one topological gap. And as I said, we checked different fillings. So what we found is that it can be it can happen that the gap at your Fermi level is trivial, but the right below the gap right below is topological. And this is very interesting for experimentalists, because just with a little bit of doping, we can place the topological gap at the Fermi level. But there are even materials that have all the gaps topological, like in the case of bismuth. And here is an example of a material that was believed to be topological at the Fermi level, but then they claim they found two bulk resonance, and it happens that these bulk resonance are also topological states that are protected by some crystalline symmetry. So this is very interesting, as I said, because there is a lot of topology. But it was not only that, also new topological cases appear from this study, because we got materials that were topological that we couldn't know why, and then we realized that we had the first high order TI with protected by inversion symmetry, so the first high order crystalline topologically crystalline insulator. Also, the first axionic insulator appeared from this classification. And the fragile phases that is believed to be the topological phase induced by layer graphene also came out from this elementary band representation formulation. So one would believe that this is straightforward to apply it to magnetic systems, but it was not straightforward because Vannier non-magnetic Vannier basis has an obstruction to magnetic systems. But the way to solve this problem was by finding magnetic orbitals. So instead of having orbitals that preserve time reversal symmetry with a different filling, what we have is orbitals that don't have time reversal symmetry. So with this basis, we could define again the magnetic elementary band representations. The magnetic maximal K vectors were also defined, and some other structural features that are very important for the formalism. Magnetic DFT codes do not preserve the magnetic symmetries. They only preserve spatial symmetries, so we need to develop codes to interface these DFT codes, and then the magnetic topological classification. Another problem that we had is that there are not materials, magnetic databases of materials, because magnetism is something very complicated, as we know. So we had to use the one that we know, that is placed in Bilbao. They have of the order of 1,000 materials whose magnetic structure has been resolved with neutron scattering. So we didn't have to calculate the ground state, because with DFT the ground state can be wrong. So we analyze these materials for different values of U and J. So we create a phase diagram to make sure that whenever we have a topological phase, we can define also parameters where it can exist. And well, I think there were of the order of 25 magnetic topological materials that were topological for the full phase diagram. And these are some examples. This is an interferomagnetic high order TI. The counterpart with neodymium, and the neodymium visible has been grown and measured, and it's published. This was the antiferromagnetic semi-metal, I think. But I know we have these band structures that actually look very nice, with very interesting surface state. Here we have the Higgs state. Here we have the Fermi arcs, and the Dirac point. So yeah, this should be the experimental signatures that one should find. And again, new magnetic phases appear, like different formulations of actions, because actually what we found with this work is that actions are magnetic high order TIs. So depending on the symmetry, one can have different spin polarized or states. All right. So everybody complains always about DFT, that it has many perks and flaws, and it's true, but this is the formalism that everyone uses when we want to deal with materials. And it happens that DFT sometimes works when people was expecting it not to work. And this is the case of some heavy fermions that now that we are working with Silke, we compare DFT with DMFT, and we don't see much difference, but DFT keeps the crystalline symmetries, and we can perform this topological quantum chemistry analysis, whether DMFT for the moment doesn't do it. And I started thinking about heavy fermions when I discovered this cumulative topology, the fact that you can have different gaps that are topological, because in the end, when we have heavy fermions, what might happen is that we'll have V bands crossed by F bands, and if it happens that the F and V bands for inversion symmetric system are in the same microposition, they are gonna gap. And if they gap, since the gap is so small, there are many chances that we're gonna have many topological gaps. But now we needed to find a material that actually could work with DFT. And the candidate that I thought was Samarium hexaboride, because it's the one everybody's talking about, but also because it happens that the topological surface state were measured. And I was thinking whether with DFT we can actually see this topological surface. And so the interesting thing of Samarium hexaboride and why we could use DFT is the following. So Samarium hexaboride is a mixed valence. I think the community has reached an agreement. So the F electrons oscillate between 5F and F5 and F6. And it happens that whenever we have two electron sorts from the half billion in this system, if we look at the symmetries of the multiplex of the Samarium hexaboride, it happens that when we apply the the three hand rules, they are j equal to 5 halves or 7 halves, and are exactly the same to the j's that we find in the single particle system, which means that the symmetry of the bands is the same. So in this case, this could be the explanation why we're going to actually apply DFT and why it works, because the bands have the same symmetry. And so we calculate the Samarian bands with DFT, with different pseudo-potentials, calculate the irrev, check that for every pseudo-potential we get the same irrev, it was the case, and we apply our formalism, and it happens that Samarian X our right has several topological gaps. These are the symmetry indicators. So the one below the Fermi level is topological, one at the Fermi level is topological, and the one above the Fermi level is also topological. And if we look at these indices here, we have the C2 and the C4 index equal to 1, which means it has a strong topology, but it also has a C4 PM index equal to 4, which means that it has a Mirror number 2. So we develop a tight winding model that is in this paper. We calculate the winding of the Wilson loops, and exactly we found the number equal 1. And we see that at the surface we can find a surface state at gamma and another one at x, which is exactly what was measured here.
Wow.
Yes.
5 minutes.
5 minutes. Oh, I'm gonna finish before I finish. So I spoke already only 20 minutes.
Yeah.
All right. Phonons. So can we have topological phonons? Yes, we can have topological phonons, and the proof of principle was given by a student in San Sebastian, Martin Gutierrez Amigo. He did an analysis of the 2D honeycomb, Bactal honeycomb lattice, and we found that actually he calculated the Wilson loops, and actually that phonons could exist. So then we developed the same algorithm. Of course, phonons are way more tricky to calculate than electrons, but we were very lucky because there is a phonon database in Tokyo, and the material project has another phonon database. So we just took the output from those databases, and we just did the symmetry analysis. So topological phonon exists. They are less than topological electrons because time reversal symmetry squares 2 + 1. So there are many topological phases that are missing, but we can find a strong topology protected by crystalline phases. And everything is in this topological quantum chemistry database, all the magnetic, non-magnetic, and the phonons, and there's another database for flat bands. So you can find the material that you want. And in any case, if the material is not there, all the codes you need to diagnose topology with these methods are available. So there's the Brian zone, the crystal structure, fan structure. Now it's implemented with and without the spinor recoupling, the gaps, the reds. When we break some symmetries, the groups of group transition, and the topology one can find there. Okay, so we can claim we understood quantum topology very deeply, at least as deep as we could. There is more topology in nature than expected. There are new topological phases in magnetic and non-magnetic materials. Okay, typically applied topological phonon. This I don't know. It's some copy paste so fun. And topological quantum chemistry can also work for heavy Fermion system, and I thank you all for your attention. This is a 100% theoretical work, so they are not experimentalists, but these are all the theory collaborators.
What is topological phonon mean?
Topological phonon mean in what sense?
Well, I mean, The typical phonons are sort of the bosons, right? So they, I mean, does it mean only, vibrate in one direction or what? Yeah, I'm trying to.
No, you can have an acoustic state.
Hmm?
You can have an acoustic state.
I don't know the one-hand function.
You can have, I mean, you can have hybrids. They claim in the,
Acoustic phonon, how can acoustic phonon be a topological?
well, because it depends how it oscillates, right?
I mean, yeah, three modes, yeah.
Yeah, it depends how the modes are positioned. It might oscillate in a trivial and non-trivial way, and you can have an X state, which is a thermal X state. It's not an
Are
electric.
there examples of this?
Theoretically, yes.
Oh, okay.
So in alpha ruthenium trichloride, there are risky dielectric effects. So there are experiments where people think about the edge transport coming from this type of.
Edge coming from
Well,
phonon.
they actually expect magnons, but it's similar. It's a
No, the magna I can understand when you have a direct gap, right? You can have but that's because you have a spin only rotated in one direction.
Right.
For acoustic, optical in the other direction. So when you open up a gap and cause energy to transfer, you have edge mode, right? But phonon, something like, phonon cannot have a gap, right?
You can have a gap.
No, I mean, not the gamma point. You can have a gap at the optical points.
No, you can have gaps and broken gaps.
A gamma point, some velocity go to zero.
I mean, not where the modes are, but after in the diffraction.
I don't think phonons can have, I mean, at least solid state physics tell us phonon cannot have a gap at the gamma point.
Well, in the quantum spectrum are no gaps.
Hmm?
But
Yeah,
there
yeah, but all the high energies, but as you, the acoustic mode cannot have a gap.
yeah, I'm not saying that you can have X states in the acoustic mode. I'm saying that there are acoustic X states in acoustic systems, so the phonons work in the same way.
Oh, it's magnets.
Yeah, for example.
I mean, yeah. That'd be very interesting if that's the case. Yeah.
Because the techno phonons are bosons, and I wanted to do the comparison with other systems. So acoustic system can have X states in the same way as phonons are.
I guess in the engineer, this metamaterials people talk about this also.
Yeah,
Classical systems.
yeah, it's mathematical system.
So they have some mechanical oscillators and they can create topological states out of it.
You mean ultramagnetism? No.
No, these are mechanical systems, like some oscillators. These are classical systems. They can create edge propagating modes by coupling them.
You can also do that in microwave cavities.
Yeah, so there are many classical systems where you can get these edge states and all that.
Yeah, you would, phonon does that. You can.
How you had a question?
It's the same question.
I do have one question. So can the TQC help us identify appropriate response functions?
If the Vanier function can help you, it can help you.
Okay.
But the TQC which are the elementary one representation are directly related to the Vanier functions. Actually, what we learn from elementary one representation is the exact Vanier basis we need to Vanierize our Hamiltonian. So if analysis of the Vanier basis help you, then yes, it can help you.
Okay. Thank you. Let's thank this.